All right, welcome everyone. Today we're going to be talking about a very fun topic called the minimum spanning tree. The algorithm we're going to study is a famous greedy algorithm by Joseph Kruskal from 1956, so cutting edge. Okay. So this problem is a very well-known problem. You can find it on Wikipedia, etc. On the textbook. In the textbook, it's in section 5.5. Okay. So what is the problem we're trying to solve? We are given a graph. The graph is undirected, but it's weighted. So all the edges have a weight. And we want to find a spanning tree. So that means the tree that spans all the nodes in the graph. So it's not just limited to one part of the graph, but it spans the entire graph. All the edges come from the graph, but of course we don't take all the edges of the graph, otherwise we would have cycles, or we would have cycles. And we want to find a spanning tree, and we want to find the one that has the minimum weight. So the weight of the tree is defined simply as the sum of the weights of the edges that you do select in that tree. And we select the minimum spanning tree here. Maybe better it would be called the minimum weight spanning tree, but just for short and because it's so well known, minimum spanning tree is perfectly unambiguously understood to be what it is. The minimum spanning tree may not be unique. Maybe you have multiple minimum spanning trees, in which case find any one. Although it is well known that if all the graph edges have unique weights, so the way weights are all distinct, then you will have a unique minimum spanning tree, and you can easily prove that as well. But if there are edges that have multiple edges that have the same weight, then you can certainly have more than one minimum spanning tree as well. Okay. Minimum spanning tree is a very well motivated problem. In fact, first time, and it was one of the times when it was formulated earlier, was I believe in the 20s, was to form for the electrification. So that means you're trying to connect all the locations of a region, specifically Morava in Eastern Europe, in Czech Republic, where you were trying to connect all the locations to one electricity grid, and you wanted to do that in a cheapest way. So in that context, the weight represented the cost, the specifically human cost of connecting those two locations. Okay. So the specific algorithm that we have here is a well-known greedy algorithm, and because we're simply trying to select the smaller edge weights here, smaller weight edges here, we simply sort the edges from E1 through EM in the order of the weight, and we initialize the counter to 0, the tree to empty, and while we don't have n minus 1 edges, we simply check would adding an edge create a cycle? If not, simply select that edge. So once you have collected n minus 1 edges, you have a spanning tree. Because a tree of n vertices is going to have n minus 1 edges, you can stop, and that's the simple algorithm. So the algorithm itself is very, very, very easily written here in a few lines. And if we take a little time complexity view of it, there are parts that we easily know how to do. We know how to sort, we know how to initialize, we can do some counter. But the part that we have to look a little closer into is, how would we track, does adding an edge EJ create a cycle? And if not, how do we add edge EJ? Does that cost us any extra work, etc., or not, right? So the main observation here that you have to make is that tracking cycles may not be that simple. So one of the basic issues is that when you're considering an edge UV, if you have, now it's possible that you say, hey, I've never even seen this vertex U before. Maybe you put a little mark on it, 0, 1, and you say, hey, this vertex U has a 0 mark. That means I've never even seen the vertex U. So of course, I can add that edge UV without any problem. But maybe both U and V are marked. That means you have seen them, but maybe they're not connected yet. So that means you should take this edge, but how would you know whether they're connected or not? So that's the real main issue here to consider, that when considering an edge UV, we don't really know if U is already connected to V using some path or not, or we at least have to check. And if we were to simply do a search or a path, that would take order and time, and that would take too long. So that's basically the main thing that you can try with array, you can try with binary search tree or heap. But again, all of them will either falter on not being able to check, or when you check, but then when you take that edge, that means now you have to merge something, then you'll end up doing a little merge on the BST, which will just take too long. So you don't really have a ready way to do that in those data structures. So that is the main problem here. So other than that problem, we know how to do this part. So that's going to take m log n time. And if this could take log n time, we would be okay. But we have to do carefully. So the main observation that you want to make here is that even though this problem is not written in terms of set and membership, actually this becomes a set membership kind of problem here. So that means that we should try to use the union find data structure. So let's do a little sidetrack on the union find data structure, even though there's a separate video as well in which we have covered the union find data structure. But let's introduce it first, and then we'll go back to the Kruskal's algorithm. In the union find data structure, each set is marked by a leader, that's a root node. And when you call the find on a set's member, it returns the leader. The leader maintains a rank or a height. Height is a close equivalent to rank here, but rank has some small subtle differences from height. So rank is a new concept that we're using here. And when you do a union, you make the tree with the smaller rank to be child of the tree with the larger rank. And this is not a binary tree. It may look like, we may think it's a binary tree. In fact, your union find data structure can look like this, in which case you can see that you are this node has 5 child nodes, which won't happen in a binary tree here. So what does this union find data structure represent at this point? What it represents is that all of these vertices here have been connected into one component. These 3 vertices have been connected into one component, and these 2 vertices are sort of hanging by themselves yet. So now if we want to connect this vertex with this vertex, we will be able to say, hey, you are part of the same component because you are part of this set here. So we cannot take this edge. Versus if we were to take this one, if we were to connect this vertex here and this vertex here, we would say, yeah, that's fine. This one here, this one here, and this one here is okay. Similarly, this one here, this one here is okay, versus this one and this one is not okay. So that's the main thing that the union find brings to you. And now if we go back to the Kruskal's algorithm, we can see that when it's written in union find terms, it can actually be written very equivalently as something very similar. Sort the edges, and for each edge in that order, check if the U and the V have the same leader node here. That's a find set. And if it is not, then take that edge and then do a union. Okay. Now using the union and the find, both of those operations run in faster than log n time, but for this perspective, log n is sufficient. So therefore, the entire algorithm can run in m log n time here. So both the two find operations and the union operation take less than log n time. So therefore, the overall time will be m log n. We note that this cutting edge algorithm actually has the same exact time complexity as an even more cutting edge algorithm from Borufka, which was from 1926, and they both run in m log n time. But Kruskal's algorithm is a well-known algorithm within the greedy algorithm family there. So that's a little summary for you. Kruskal's algorithm, simple, easy to implement algorithm. Find the minimum spanning tree in m log n time. That's all I have for you today. So enjoy, keep